Hello friends, for next 20 minutes or so, we are focusing on basic concepts and fundamentals used in shear force and bending moment diagram and their applications. But before going to shear force and bending moment diagram, some prerequisites we have to understand. Let's go one by one. First is resolution of force and moment of force about a point. If I wish to resolve a force in orthogonal components, then we have been supplied with the force in magnitude and direction. Then for the direction theta, the adjacent component is always cos component and other component is always sin component. That means whichever the component adjacent to angle theta, that is always cos, and remaining component is sin component. Now to take the moment of force, point force about any point, suppose I consider a point A about which all the moments of these three forces 1, 2 and 3 I wish to take. Then how to take the moment? Already we have covered all these things in equilibrium, but one more time some recap we will do. Basically sign convention used in equilibrium condition is anti-clockwise positive, right? And I am interested to take the moment of force of 2 kN about point A. So for vertical is the force, horizontal is the distance required, which is perpendicular distance. So moment of this 2 kN force is 2 into perpendicular distance is 1.5. Observe that it is clockwise, so it is minus. So moment is minus 2 into 1.5 about point A. Now second force is that inclined force of 5 kN here. Now first of all, I will resolve this force because it is inclined. I will resolve it is in horizontal component and one vertical component. We know that the horizontal component is adjacent to angle 40. So this component will be 5 cos 40, and observe that the 5 cos 40 component is passes through the point A. Whenever any force passes through the point, its moment about that particular point will be 0. So this 5 cos 40 force will create 0 moment about point A. Now let us think about vertical component, that is 5 sin 40. Vertical component means horizontal is the perpendicular distance required. So that overall distance from point A is 1.5 plus 2, it is 3.5. So force is 5 sin 40 and distance is 3.5. Again, according to the arrow, we observe that it is a clockwise moment about point A. So it is minus 5 sin 40 is the force and 3.5 is the distance. So this completes the moment of that vertical component of 5 kN. Next force is 3 kN. It is horizontal. So whenever force is horizontal, I need vertical distance as a perpendicular distance to take the moment, and that vertical distance is 0.5. Observe that the moment created is anticlockwise because arrow of the force is leftward. So this arrow will create anticlockwise moment about point A. So moment of that force is 3 into 0.5. Answer is positive because it is a anticlockwise. So 3 into 0.5 is the moment. Let's move ahead. Now let us think about distributed forces. Distributed forces means those have distributed effect on certain distance on area or length. Here observe that there is a rectangular load, or we can call it as a UDL, uniformly distributed load, which is distributed over portion BC of 3 meter length. So for a rectangle, it will be centroid will be at half distance. So from this point to centroid point, distance is 1.5, and the force here acting is intensity is 8 and distance is 3. So total rectangular force is 24 kilonewton. Now I want to take moment about point A, so I need this distance. Fine. So that distance equal to 0.5 plus this 1.5, so it is 2. So 8 into 3 is the force and 2 is the distance, and it creates again clockwise effect. So moment is minus 8 into 3 is the total UDL and distance is 2. So that will be the moment of that UDL about point A. Next force is triangular load, or uniformly varying load, UVL. In case of UVL, you observe that the shape is triangular shape, and for triangle, the centroid will act as 1/3 from 90-degree angle. So this is our 90-degree angle. From that 90-degree angle, this distance is 1/3. 1/3 of 3 means it is 1 meter. So this distance from this point to centroid point, distance is 1 meter, and the remaining distance is 2/3, that is 2 meter. 2/3 of 3, that means 2 meter. Total UVL is acting at centroid point, and at the triangular shape, the value will be 1/2 into intensity, that is 4, and base distance is 3. So this is equal to 6. Again, for this vertical force, I need this particular distance, and that distance is equal to 0.5 plus 1 from point A. So total load is 1/2 into 4 into 3. Distance is 0.5 plus 1, that is from point A. So this is 1.5 is the distance, and this is the total uniformly varying load. The sign is minus because it creates a clockwise effect. The sign should be minus. So this is the way how the moment of forces and UDS can be taken about a point. Third prerequisite required is types of beams and types of support reactions. And last one is applications of equilibrium conditions whenever we need to find support reactions. These two particular points we are going to cover when solving the problem in session 2. Let's consider a member which is fixed at left end, and for this member, this axis is called as longitudinal axis, and this axis are called as lateral axis, which we are saying it as X and Y, and this Z axis will be the longitudinal axis. If suppose any force is acting lateral to the member, lateral means perpendicular to the axis of member. Whenever force is acting lateral to member, there are two types of effects we can normally observe. One is this. Observe that the portion ABCD, which is shown by hatched line, that are sliding over each other. Such a sliding effect is called as shear effect. So internally active force causing sections to slide, that is called as shear force. Now let us consider same member subjected to same lateral force, but now the effect is different. The second effect may be something like this. Now observe that here is the member bends, and whenever any member bends, the portion ABCD, this particular section, is rotated. Initially you observe here it is initially in vertical plane, but now here it is inclined. So that inclined effect or rotation effect of the section, that is called as bending action. So bending moment is nothing but internally developed moment causing sections to rotate. Now these are some fundamentals in which the relation between loading on beam, shear force and bending moment are to be expressed. If we understand this effectively, then our job made simple to identify what is the shape and what is the nature of shear force and bending moment diagram. Consider a beam AB, which is represented by axis X, and y-axis will represent loading rate. So some distributed load I have considered, and now consider two sections, one is at C and one is at D, dx distance apart, a short differential distance, and at section X. If I enlarge that CD portion, it will be look like this, and as we know, at section D and at section C there are some shear force acting and there is some bending moment acting. Let's consider shear force V acting at C, and there is slight increment in shear force at another section V plus dV, because the section C and D are different sections. So slight increment is there. Similarly, consider also bending moment. So bending moment at C, section C is M, and there is such increment in bending moment at section D, that is M plus dN. Now if I apply equilibrium conditions which is applicable here, so there are two equilibrium conditions are applicable. One is summation Fy equal to 0. So writing the equation in the equilibrium form and reducing it to these values. Observe, this is the first relation we are getting. The derivative of shear force is nothing but rate of loading. If I transfer the variables, I will come to know that dV equal to W dx. If I take integration on left both sides, then it is clear meaning that the area of loading diagram or integration of the loading gives me change in shear force. So these two relations are very important, which gives me a concluding form. First conclusion is derivative of shear force gives rate of loading. In other words, one can say slope of shear force equal to loading rate. And second is the change in shear force, if I wish to obtain, then I have to take loading diagram area, either left of the section or right of the section. So that is the first case. Now second case is regarding relation between shear force and bending moment. Again I will consider same case, but now the remaining equilibrium condition is applied, that is moment about any point equal to 0. For my simplicity purpose, I have selected point D to take the moment, and this is the moment equation written with the sign convention as usual, that is anticlockwise positive. In this equation, you observe this term, it is a fractional term because dx square is a very fractional term, so it can be neglected from the equation, and solving remaining we get relation like this. dm by dx equal to v, that means derivative of bending moment gives me value of the shear force. By transferring the variables, and if I take the integral, one can understand that area of shear diagram is nothing but change in the bending moment. So these two relations are important here. So that gives me two conclusions. One is derivative of bending moment gives SF, slope of bending moment, and second is if I transfer the variables, then change in bending moment is nothing but area under shear force diagram. But whenever you have to take area, you should consider either left part of the section or right of the part of the section where you are going to consider the point. So based on the above relations, I come to know that simple equations. When loading rate is known to me, I would say dV by dx is equal to rate of loading, and dm by dx is equal to shear force. From these two derivations or relations, there are some key points we need to understand and we need to remember that. First is shear force. Mathematically, one can say shear force is algebraic sum of lateral forces either left of the section or right of the section taken with proper sign convention. Let me clear what is the meaning of section left and section right. Suppose if I take a beam, something like this, simply supported beam, and it carries some loads, maybe UDL or UVL, and if I take a section here, that means I wish to calculate shear force at this particular point, then I have to consider either left part or I have to consider either right part. So either of the one part I have to consider, either left of the section or right of the section, and with proper sign convention I have to consider. This is the sign convention we are going to consider for shear force. If I take sections, this is the green line gives you section. If I take sections left part, then upward is positive and downward is negative. And if you are going to consider sections right part, then downward is positive and upward is negative. But I would suggest you to remember one simple form, this one. Sections left, upward, and sections right, downward. That should be taken as a positive. So if I take simple convention, sections left up and right down, positive. Second is the graphical representation of shear force values plotted along the axis of member is called as shear force diagram. How to plot that diagram we will see in the problems. And third is the shape of SFD is governed by rate of loading on the beam. Definitely, because we have one relation derived, that is dV by dx is equal to rate of loading. So definitely, depending upon rate of loading, the shape of shear force diagram varies. How actually it varies, we are going to see now one by one. Basically, if I think about the loading, there are two types of effects of loading. One is concentrated effective load and second is distributed load. So focus one by one. Concentrated load. In that concentrated load, there are two varieties again. One is concentrated point load or second is couple acting at a point. So whenever concentrated point load is there, because of that point load, shear force diagram has sudden change like this. Sudden rise or fall is there. And you observe that whenever load is acting downward, it is the fall. And whenever load is acting upward, it is sudden rise. So that particular point you remember in mind, that whenever shear force diagram has point load, the SFD is sudden fall or sudden rise depending upon downward or upward. And also interesting point is that the total height of the rise or fall, observe this height. So this is 4 below baseline and 1 above baseline. So this total is 5. The rise or fall height is always equal to magnitude of the force. So if the force is 5, SF diagram has total change of 5. Fine. But whenever couple is acting on beam, as couple comes under the moment effect, it will not cause any change in shear force diagram. So observe that there is one couple acting at point E, but when I am considering shear force diagram, then at point E there is no effect at all. So couple does not have any calculation change or effect on shear force diagram. Fine. Let's move ahead to distributed load. Distributed load means either there is no load at all, that means zero load or no load, or either there may be UDL or UVL. In case of no load, observe here, DE portion does not have any load. So no load means W equal to 0. And we know that integration of W nothing but change in shear force. So integration of 0 is constant line. So that's why shear force diagram is a constant line here. That is the first part. Second part, whenever there is a UDL, so UDL means constant line. That means W is something constant. And for constant, integration is X. So X means what? Inclined line. So shear force diagram is an inclined line. Only point to understand is whether the inclined line goes down slope or up slope. It all depends upon type of UDL. If the UDL is acting downward, the SFD is down slope, and if UDL is acting upward, SFD is up slope. Third point is UVL is acting. Now UVL has many varieties. That means UVL may be decreasing downward or increasing upward or something like that. Now one by one I will consider. First of all, what to happen with UVL? Whenever say UVL, W is something like 3 times X. That means it is a linear equation. And for linear equation, if I take the integration, it will be X square. Right? So X square means what? Parabolic curve. So concept is whenever UVL is acting on beam, the shear force diagram is second degree curve, parabolic curve. Only point to understand is for that parabolic curve, whether the concavity upward I should draw or concavity downward I should draw. And for that, this simple format we have to remember. UVL downward increasing, UVL downward increasing, something like this. This is a UVL increasing, right? Increasing UVL and downward. In that case, the second degree curve concavity down we have to plot. So if I want to join these 2 points, then it should be like this. So here is the concavity down. Similarly, when UDL downward but decreasing, observe here, this is the downward UVL, but it is decreasing. In that case, concavity is drawn upward. So this is the concavity. Like that, if you remember these 4, it is very easy to plot shear force diagram. Now regarding bending moment diagram, again mathematical definition will be bending moment is algebraic sum of moments, because it's a moment. So algebraic sum of moments taken at a section due to lateral forces either left or right of the section with proper sign convention. Again the same concept you remind. What I mean to say, left of the section or right of the section we have to consider with proper sign convention. And sign convention for bending moment is very simple. There are 2 technical names are given: sagging moment, which is taken as positive, and hogging moment, which is taken as negative. Let us understand what is that sagging and hogging. If I take a bar something like this, and if I wish to bend that bar in a shape of smile face, so you observe that this is a smile face, and if I want to bend like this smile face, I should apply moment like this and like this. So then it will become sagging shape. So this is a smile shape. So one can say if this is the section line, then moment like this on left side and moment like this on right side, that is a sagging shape. Correct? One can understand, say, smile and cry or happy and sad. Another concept is if I take a section like this, then moment going out like this are positive and if I take section like this, then moments coming in may be taken as negative. So all this meaning is same. Whatever you feel simpler, you can remember. But I would suggest you happy and sad, or you can say in and out. That is best possible method to remember the sign convention. Then graphical representation of Bm values plotted along the axis of member is called bending moment diagram, that we are going to see in problems, as I said earlier. Again, the shape of BMD is governed by rate of SFD. Definitely, because we have seen one relation, dm by dx is nothing but rate of loading. In other words, if I transfer the variable like this, dx integration, that is equal to change in moment. So integration of shear gives me change in moment. Let's see how that effect under various types of loading on beam. Again we will consider that two effect, concentrated and couple. Now in case of concentrated point load, the bending moment diagram does not have any change, because if I take section at C and observe this 5 kN load which is exactly passing through point C, in such case we already seen that whenever point load passes through the point, it does not have any effect on moment. Therefore, whenever point load act on beam, BM does not have any change. That is first point to understand. But in case of couple, definitely couple will cause sudden change or sudden rise or fall in bending moment diagram. So this is the couple here, and in couple you observe that there is an anti-clockwise couple acting. So whenever anti-clockwise couple is acting, there is sudden fall, and whenever clockwise couple is acting, there is sudden rise. Again, total rise or total fall of this particular line is always equal to magnitude of that couple. So it is written here, right? And it is equal to magnitude of that couple. So whatever here total height, positive 1 and negative 2, total height is 3, that is matches equal to 3. So this is the idea about the point. Let's move ahead about the distributed effect. Distributed effects are covered under 3, either no load or distributed load. Observe there is no load here, DE portion. No load means loading rate is 0. So integration of that loading rate gives me shear force. So for shear force diagram, it is a constant line. And integration of shear force gives me bending moment. So for bending moment, integration of constant becomes x. That means no load, SFD is constant, horizontal line, and BMD is x means inclined line. So that is the idea how we go from top to down by integrating and bottom to top by differentiating. Zero load, constant line, sloping line. In the similar fashion, constant line, inclined line, parabolic curve. That means whenever distributed load is acting, uniform distributed load, SFD is inclined line, because for constant UDL, SF is inclined line integration, and for inclined line integration is parabolic curve of second degree, so it is parabola. Only point we have to understand that whenever we draw second degree curve or third degree curve, whatever, we have to think about concavity up or down. So in case of BMD, it is very easy to understand. Whenever any distributed load acting downward, concavity is always acting down, and whenever any distributed load is acting upward, concavity of BMD is always up. That will remain same for the next case also. Whenever UVL is acting, there is also concavity up or down, depending upon same thing. I will show in next slide about this one. But one interesting point we have to observe here. See, think about this particular point, G point, where shear force equal to 0. And we have already know that dm by dx is nothing but shear force. So whenever any derivative becomes 0, that particular function may have maximum value or peak value. That is written here. Whenever there is a 0 shear point like G, at that particular point, this particular bending moment is peak value. Observe here also, for H point, there is a 0 shear point, and if I extend that point here, the bending moment diagram has peak value. So that particular point, again, we have to focus it off. See here, as I said, whenever UVL is acting downward, BMD is concave down, UDL is acting up, UVL is acting upward, BMD is concavity up. So simple point to remember regarding this one. But one more interesting point we have to think that whenever BMD crosses the point here, right, at this particular point bending moment changes its sign from positive to negative. Such particular point where bending moment is 0 and changing its sagging to hugging nature, that particular point is called as point of contraflexure, right? So friends, we are now coming to conclusion part. In previous sessions, slides, we seen the fundamental relation between shear, loading and bending, and what is the general nature, how to guess this SFD and BMD, what should be the nature of the SFD and BMD we have seen. That wrap up I am taking here, properties of SFD and BMD, that already we have discussed that area of shear force diagram either left or right of the section is nothing but bending moment, and slope of bending moment diagram gives me shear force at that point, and definitely slope of shear force diagram giving me loading at that point. That means we are going from bottom to top by derivatives, and as I said, when you come from loading diagram to bending moment diagram, you are going by integration way. Similarly, the maximum moment occurs at a point of zero shear, that already I have discussed, and when shear force diagram is increasing, or one can say when UDL is acting upward or UDL, then moment diagram is concave upward. This is simple nature we have discussed earlier. Now these are the general steps which are followed to plot shear force and bending moment diagram. The first step is as usual, draw a FBD of given beam and find reactions of all the supports whatever they are given. With proper sign convention we have to use. Here the sign convention of equilibrium we have to use. So for the first step we are using summation Fy upward positive, summation Fx rightward positive, and summation moment anticlockwise positive, because these three are the basic sign conventions what we learned in first year mechanics. So these equilibrium sign conventions we are going to use for first step. And second step is calculation of shear force values. As I said, either left or right of the section part we have to consider. Then calculation of bending moment values we have to do for, and next last point will be, if at all any their point of contraflexure is there where shear bending moment diagram changes its sign from positive to negative or negative to positive, how to locate that point and how to find out zero shear point and their maximum values at bending moment.